data prediction of deflection basin evolution of asphalt pavement structure based on multi-level neural network. I am from China, Southeast University. Here we begin. I'm at reducing the high cost of data collection of deflection basin in the structure design of asphalt pavement and shortening the longest time of new structure. This paper this paper designs a structure encoding network based on traditional neural network to map the pavement structure and an abstract space. Therefore, generalization ability of the neural network structure is improved, and a new multi-level neural network model is formed to predict the evolution data of the deflection basin of the untested structure. By testing the experimental data of the RIOHTRACK, the network structure predicts the deflection basin data of untested pavement structure, of which the average prediction error is less than 5%. In the past 20 years, Europe and the United States have established the concept of long-life pavement. Long-life pavement refers to a pavement where the foundation or pavement base layer will not be significantly aged under the condition of the correct pavement maintenance. Most of the traditional pavements are sync-grid-based asphalt pavements, which have advantages of good stability, the convenient material, but there are also disadvantages of poor durability and high maintenance cost. Traditional asphalt pavement has structural damage, many manifest as a fatigue correct many manifest as a fatigue cracking and pavement and permanent deformation, which has a short serve life, and the demanding and reconstruction have brought huge economic loss. In order to reduce the maintenance and other costs in the future, it will be more cost-effectively to extend the design life of the roads and the place in the heavy traffic to at least 40 years without the need of stressing the structure. Many existing literatures analyze the fatigue of pavement structure through mechanics tests and study the corresponding factors that affects the pavement mechanics. Yu et al. Carried out a four-point bending fatigue test in the consistent strain and the constant strains models, and established the laboratory fatigue prediction model in these two cases. In addition, the transfer function of the loading model is established to realize the fatigue life conversion. Moreover, laboratory constant strain prediction model was combined with the loading model transfer function to establish an asphalt pavement fatigue correct prediction model. With the development of machine learning, the application of artificial neural network has grown tremendously in various fields of energy, such as road condition and performance prediction, road pressure prediction, and structural road system evolution. Gu et al. Applied artificial neural network to predict the response of any given material and the structural characters to gene-reinforced pavement. Furthermore, the results are applied to the method of improving material performance in pavement design, so as to consider the influence of enforcement on the pavement design under any traffic load and the weather condition. RIOHTRACK was utilized, the RIOHTRACK was utilized in 2017 and to a trial loading test to collect and study the evolutionary law of multi-use performance under the condition of the full life service cycle of nonlinear road structure and materials, and to verify the improvement and improve the design method of road structures and material on the different load level. 19 kinds of structures deflection basin have been regularly as an important indicator reflecting the bearing capacity of asphalt pavement structure. Deflecting has always been focus of highway builders and scientific research. This paper uses the data collected from the RIOHTRACK ring road to predict the deflection basin of the road, and by establishing a multi-level neural network model. The main contribution of this paper is to establish a multi-level neural network model, which mainly includes three parts: encoding converter, coupler, and the integrator. The encoding converter is used to convert an original date of structure to a high-dimensional coded data, and the coded data is used as an influence factor to predict the deflection basin data of the road surface. The coupler checks whether the code data are appropriate in the high-dimensional space. The interpreter is a component that generates the prediction of the deflection basin data finally. As mentioned before, the data in this paper was collected from RIOHTRACK. It is obviously that the cost of time, labor, and the finance of such a test are very huge. From the deflection basin of untested pavement structure, even if an abstract physical model is established to simulate the deflection basin data, it is quite difficult to calculate. The research in this paper is based on 19 kinds of experimental pavement data of structure and the corresponding other data, including temperature, load, number of standard extra load, and the deflection base. It is expected to directly predict the performance of the new pavement structure composed of the structure materials involved the existing pavement without paving the new test road, so as to save the pavement research cycle and their costs. In order to achieve the above goals, this paper established a new multi-level neural network model consisting of encoding converter, coupler, and the interpreter. Use the known structure to train the model. The prediction of the test data of the new structure is completed. Here will come from the definition and the framework. This paper mainly predicts the pavement of deflection by extracting and encoding the construction features of pavement and combining with other features. The different structures related to each other form a tuple represented by the node G, which equals the tuple V, E, and X, where G is the couple V and E constitutes the graph. Now V represents the set of nodes in the graph that is the set of different pavement structure. E is the set of edges between the nodes, and X is the characteristic of the nodes, where xi is a real valued vector. The characteristic of the node is in this paper is the deflection basin performance of the pavement structure. In essence, E represents the relationship between different structures, which can be determined by their pavement structure and the deflection base. That is, E, V, and X. A method F star is expected to be a fund of is expected to be found in to encode the structure through the training model, which satisfies the equalities below, where F represents the encoding method. The overall framework of the model is shown in Figure 1, which consists of 3 components: the encoding converter, coupler, and the integrator. The encoding converts the original pavement data into an array through the prediction pre-encoding and then encoding the further through a long short-term memory LSTM network and a linear layer. The coupler is mainly used to reconstruct the graph and the train the network. The interpreter takes a learned coding vector and other factors that affects the deflection basin as input to realize the prediction deflection basin. In this section, a multi-level neural network model is designed in details. First, the data structure past the encoding converter and the coupler to learn the potential encoding vector. Then, the learned encoding vector is used as an explanatory factor to predict the deflection base with the interpreter. Now the details model and the methodology is here. The encoding converter mainly includes 2 processes. To begin with, the original data of structure was pre-coded. The pre-coded data is shown in Table 1 as below. And they consist of the different layers from layer 1, layer 2, and layer 9. We have 19 different structures, but now we only show the 5 of them. Let the A's denote the set of all materials involved in the pavement structure in V. The numbers Sj as 1, 2, K respectively. Therefore, the material thickness and the serial number of material of each layer together constitute the pre-code matrix P, where P is in a real space whose dimension is L times 2, and L is determined by the number of construction material layers. Next, the further encoding is complete through an LSTM network and a linear layer. The linear layer is fully connected. The space of the prediction matrix is defined as the coding space F. After pre-coding matrix is converted by LSTM, the coding expression on the abstract space H is obtained, and the mapping from the coding space to abstract space is realized, and the result is denoted by ZT type. which is followed by the normalization process. Z equals WZ times ZT tight and plus BZ. Let Z be the set of Z1, 2, and N, represents the coding vector of all structures. It should be noted that the series number of structural materials in the pre-coding process can be in any order, without considering the similarity and the correlation between the material. But because the similarity and the association of structure can be reflected by the output LSTM as long as the serial number of the same material is the same. Here is a construct of an LSTM. The copper is mainly used to train the aforementioned LSTM network through a reconstruction. Verifying existing decoders can achieve structure reconstruction. In this paper, characteristics are used from reconstruction. Firstly, transform the characteristic as a follow into obtain the matrix X into the matrix M, where the DFT is the discrete Fourier transform. I is an array whose elements are all 1, and the matrix M is defined as an attribute a Jackson matrix. The encoding squeeze Z is used to obtain the reconstruction the M, and as follows. Where W and B are weight matrix and bias respectively. The reconstruction loss function is defined as LS. The interpreter, here we introduce the interpreter. First, the goal of this paper is to predict the deflection base of untested pavement. The existing results show that the deflection basin has a great relationship between the temperature, load, and the number of standard axial load, and obviously has a close relationship with the pavement structure. The features of the pavement structure have been extracted above. The coding structure sequences can reflect the structural features and the collections of different pavements. Through a simple linear regression analysis of the data, it can be seen that a clear linear relationship between the deflection basin and the load. Therefore, the same display neural network interpreter is shown in Figure 1 is designed. The input of interpreter in the encoding sequence Z, the number of standard axial and load N, and the temperature T, and the load L. In this paper, a cumulative number of the standard axial load is adopted as N. First, input Z, N, and T into a neural network to get a compressed figure G. The compressed figure G and the load T is subjected to a Hadamard product, and the dimension compression is performed through the fully connected layer to obtain the predicted deflection using the U, where the star is a Hadamard product, and it can be seen that the black box part of the network is only for the is only for the extraction of the compression feature G, and the relationship between the load and the deflection basin is fully displayed by the parameters of the fully connected layer. The final forecast error of the definition is defined as LP. Here we come to the experiments. In this section, the data is used in the experiment is introduced, and the evolution criteria of the model is explained. So as the parameter setting, the results of the experiment are analyzed after the results display. The whole experiment is incompleted by the Python and PyTouch. The data used in this paper comes from China's first forced car pavement test ring road named RIOHTRACK, as shown in Figure 3. The ring road is a closed curve divided into two sections of strain and cylinder. The total of the 19 kinds of pavement structures have been designed, including the flexible seam grid and grid base structure, as well as different asphalt structure layers of material combined models. The 19 kinds of pavement structure are divided into two sets: a training set and a test set. The training sets contain 16 structures, denoted as D, and the remaining two structures constitute test. The remaining two structures is denoted by V. By deleting the missing date after 256 dates from each pavement structure, therefore there are 4,096 data in the training stage and 512 data in the test stage. When prediction and the mean square errors are used in the evolution criteria to estimate the effectiveness of the model. The loss state of both components are MSE loss, and the learning rates are set to be 0.02. The number of the training iteration is 3,000 and 1,000 respectively. Due to the lack of the training data, the complex of coding layer is reduced. Use a single layer or LSTM and the single layer fully connected to prevent overfitting. In Figure 4, it is shown that the prediction result of the two structures STR16 and STR18 in the test set. It can be seen that the overall performance of the model proposed in this paper is well, but at some peaks it looks like a little bad. The average MSE of all the data is in the test stage is 0.0455, which also shows that the overall prediction is effective. In order to verify the importance of the encoding converter as a comparison, the predicting code structure vector is used as a directed as a predicted factor, and the factor prediction deflection based through the interpreter. In the preliminary analysis, the reason of a larger prediction error of a normal neural network is that the characters of the space in which data of structure is located are significantly different from characters of the space in which the physical quantity is being tested. The former is a logical expression space on the intuitive level or with a spatial order structure, while the latter is a physical space on a dynamic level with a temporal order structure. However, it is difficult to analyze the time sequences of a multi-level structured space, so nonlinear fitting function of the normal neural network is different to play its due role. It may be noticed that the data of structure and the one of the experimental test variable have different dimensions. Um, Consider that the different dimensions cause a larger deviation of the normal neural network prediction result. Here is a different opinion, because even in the interpreter module, the dimension of the input variables are not the same, but the multi-layer neural network proposed in this paper has a less error. At present, a large number of neural network modules can input variables of different dimensions at the same time and achieve good results, which means that a neural network model can overcome the problems caused by different dimensions to a certain extent. In this in the problem dealt with in this paper, the data of constructor is a vector and in an abstract space compared to variables such as the temperature, load, etc., which is like the direct transcoding of textual expression. The coding module and the kappa module and the kappa module proposed in this paper are similar with the function of walk-to-vector in the natural language processing. After coding is complete, the topological structure being coding between codes can better express the topological relationship between them at the time of testing, so it can directly reflect the physical meaning represented by a structure. That is, the original intuitive cognitive space is mapped to a physical space, and the consistence of the two spaces is gravitated, so that a better calculation result can be obtained. In this paper, a multi-level network model has been proposed and that can encode a data of structure and prediction the deflection basin of asphalt pavement. It can be seen from the experimental result that the structure coding is effective and important. The method proposed in this paper can use the existing data to direct predict the deflection base of untested pavement, saving the time and the capital cost of the repeated experiments, and the mean prediction loss is under 5%. However, this aim relies on a large amount of large amount of historical experimental data. Therefore, besides the present research mentioned in the discussion section above, a model development based on a small sample training is still in process. Thank you for listening. Any question is welcome.